Hill University. I'm a member of the JER group. So today I'm going to walk you briefly through some of our work. It's a part of my PhD, actually. It is kind of more sciencey geared rather than the intense geotech engineering presentations we had today. But well, I cannot promise it's gonna be interesting or that interesting. It excites me, and I'll try as much as I can to engage you within. So yeah, let's start. It's so today it's numerical modeling of groundwater-driven sand infiltration into defective sewer pipes. So basically, what we're going through is a bit of introduction and background. What are we looking at? What is the problem that we're tackling? And then we start by answering a very important question. What is the rationale for the approach and the framework we're using? And this is very important because eventually the CFD-DEM coupling, the computational fluid dynamics and discrete element modeling, both are very quite complicated, and they are not your usual go-to approaches when you want to tackle any problem, right? So when we consider coupled discrete element modeling with computational fluid dynamics, we kind of should have a strong rationale behind that. Finally, a bit of validation and parametric analysis results, and eventually some of our insights into the erosion process around gravity pipes or sewer pipes in general. So what we're looking at is a system. So at the moment, we're only looking at granular soil. So the system we're looking at is a sewer pipe that is buried in sandy soil. And at the case with its many pipes, especially with old infrastructure, the pipe can be cracked, it can be broken at many places. And if these cracks are large enough, they can allow for the sand infiltration into the pipe. Now, the problem gets worse with the existence of groundwater table above the pipe, because now we don't only have sand going into the pipe, we have sand and water both flowing into the pipe. And furthermore, the flow of sand or the erosion process is accelerated with this additional momentum that is given to it by water. So this comes with a range of detrimental effects. Start with weakening the soil around the pipe, which weakens the supporting, the existing support for the pipe and perhaps some of the surrounding infrastructure. It also, well, it can result in some cavities and ultimately some sinkholes. And as a matter of fact, many sinkholes were reported right after heavy rainfall events. So that is a sudden rise in the groundwater table. Perhaps one of the most famous of these sinkholes is the one in Guatemala City back in 2010. Now, we're not saying that this happened all of a sudden after one rainfall event, but you can imagine if the erosion process is to be accelerated around old and defective infrastructures in a place that is witnessing heavy rainfall events over and over and over. Eventually something of that magnitude might happen, and indeed we don't want that to happen. So what we're trying to do, we want to look at first getting some good understanding of the dynamics, what's happening in there. Is it a flow of a sand water mixture? Is something else going on there? So the first step is just a basic understanding of the mechanics. And then we want to quantify and also qualify some of the some of the parameters and factors involved with that process, like the variations in groundwater table, like the characteristic, the geometry of the defect, the thickness of the sand layer above the pipe, and so on. And to do that, we kind of have to go deep to the micro scale around the pipe. So, for instance, if we go into the crack level and see how the sand particles might interact around the crack, we have three scenarios. Well, first scenario is what we call a stable arch or bridging. So in that scenario, this can happen if the crack width is small or the crack is narrow enough to permit this arching effect to happen, which is a good thing because now it is stabilizing the infiltration process and it's almost preventing it. The second case, what we call a freefall arch, is kind of the dynamic balance case of the first one. So now if the crack is a little bit wider or the sand friction is a little bit, or the interparticle friction to be specific is a little less than the first case. So what happens is that this arch keeps forming and collapsing and reforming again almost instantaneously. And with that happening, it creates a case of dynamic balance where the infiltration process is not simply a continuum-like flow. It is a series of forming and collapsing of these microscale arches. And now, to give you a perspective, we are talking about things in order of millimeters, right? While the system itself, the bigger picture we're looking at is meters, maybe tens of meters, right? And eventually, one of the systems or one of the flow regimes that we can have is eventually when there is no sufficient soil cover or sand cover above the crack. So particles will simply just roll until they reach their angle of repose. So we're particularly interested in this free fall arch regime because this is when things are dynamic, and this is when sand is infiltrating in the first place. And there is something that is super interesting about this this regime. That is, well, first let me kind of give you this analogy. If we have this hourglass kind of flow, one has solid particles, kind of like sand. It's basically an hourglass of sand. I do have one to play with here. But bear with me, if you fill it with water, right? And now we're going to increase the amount of sand and water to begin with. While in water flow, we want the water flow or the outflow to increase by increasing the head above the opening. In the sand flow, it is not the case. And this actually has been known for almost 2 centuries now, and it was only quantified back in the 60s with Beverly and his collaborators. It was known as the closed vault effect, the free fall arch regime, and so on. And what's really interesting about this thing is that the erosion rate or the infiltration rate, or whatever you call it, of solid particles, it only depends on something that happens at the not micro scale per se, but a very narrow arch that we talked about just a minute ago, right? And so it doesn't really see the entire system. It sees a very localized point or domain about the crack. Now, if we're to model something like this, we can do that using discrete element modeling. But if we want to include water in the game, we have to add a computational fluid dynamics component. And not to bore you with a lot of equations and such calculations, but the whole idea is that we are solving the equations of motions about the solid particles. So the overall numerical consideration of the problem is that we have this kind of Eulerian or continuum-based mesh of water. And within, we're considering a Lagrangian treatment of the solid particles, right? So as we solve the equations of motions for the solid particles and the volume average Navier-Stokes equations for the water flow, we're making use of these two terms that are kind of the momentum transfer, or what we call the particle fluid interaction forces. These forces are drag forces. They could be many actually, like a set of forces, but mainly drag and buoyancy forces. Right. So this is mainly the essence of the method. So let's go back to our problem with the sand erosion. So first, we decided to take a validation case just to make sure that the model is producing comparable results and satisfactory results to what we expect. The system we're considering is a bed of sand submerged underwater. And at the bottom of this box, there is a pipe with a rectangular slot. So it's kind of more or less two-dimensional flow, right? And as this slot opens, both water and sand can start to infiltrate through the slot. And the quantities we're measuring here are both water flow, sand flow, the physical deformation of the surface of the sand, and so on, and maybe any internal cavities that that develop. So this is more kind of the general setup that we're working with, and at the same time, very close to the experimental setup used by Tang and his collaborators in 2017. On the right-hand side here, you can see our CFDM simulations compared to the experimental data. And IOC is actually quite a decent comparison. I'm sorry, pardon me. So initially, we have some mobilization at very early times of the upper part of the bed above the pipe, and then kind of like a narrower core starts to get mobilized, and at 10 seconds of simulation, we can see our model could even capture the V notch of erosion that happened in the experiment quite decently, as well as to a good extent the velocity distribution in the bed, right? Something that is really interesting here about this kind of, because this is not the only experimental work that has been done on this problem, but what is really interesting that people always examine the effect of groundwater by introducing a submerged bed and then keep increasing or decreasing sometimes the water head above the sand. Quite surprisingly, nobody starts the test with dry sand. And so a very fundamental and basic question remains unanswered as to what happens when we introduce water in the first place. We generally do not expect the water table to be above the pipe, and that is going to happen probably in some specific events. So we need to answer this basic question on mobilization. And this is why, ahead of everything, we just carried out an analysis case of pure discrete element modeling to see what happens in the dry case. And so here, if you look at the right-hand side, we have the graphs for the total eroded mass over time. So this is the amount of sand that is lost from the system over time. And this purple line represents the dry case. What we notice, which is rather expected, is that in all cases, when groundwater is involved, we have more sand erosion than what we have in the dry case, which was not actually kind of a self-evident question. But what is really interesting here that when we increase the waterhead above the sand, we kind of have like a converging effect, kind of like the effect of groundwater is diminishing. For instance, 0.3 and 0.4 are almost identical. 0.5 is almost identical to 0.4, which might be counterintuitive at the beginning, and we actually are still investigating the mathematics and the phenomenon behind that. But it actually, when we had these results, it brought us to quite it was reported quite often that increasing the waterhead above the pipe or above the sand level does not have a tangible effect on the erosion rate of sand. For instance, Go and Ju in 2017 and Tang 2017, Zhao 2018, they all reported no tangible effect when we increase the water level. But now we're making a stop with saying, hey, you guys, well, looking at their experiments, they started the experiment with a rather high water level compared to the dry case, as we see. So as they go on increasing the water level in the experiment, you can see they already are in this converged area where there is no really tangible difference, which was quite an insight when we got these results. So these results are for a crack located at the pipe ground. Now, what happens if we have inclined cracks? So in this case, the direction of momentum is no longer, or the driving force given by water, no longer aligns with the gravity. So we'd expect slower kind of flow, right? Which exactly what we see. So here, theta equals 90, that is the vertical or the crown crack. As we go away from the vertical, we have slower rate of erosion. But what is very interesting is that even underwater, the sand is going always to end on its natural angle of repose. So it reduces to a matter of simple geometry to basically say, hey, yes, but it will certainly result in more eroded mass. So although this crack will erode a slower rate, is gonna result in more mass, but it doesn't stop here. It's not only the increase in the eroded mass that concerned us. It is the mobilization of what we call a dormant crack. So to give you a perspective of that, here are the simulation cases for dry and wet inclined cracks. Let's take the first two, for example. The crack width is about 8 millimeters. So although 8 millimeters, and if it was a vertical crack, it would permit particles to infiltrate the to filtrate through the crack. But with us deviating the crack from the vertical, we are more likely to get a stable arch effect, even though the particles are within the comparable range of infiltrating. But what happens when we introduce water is that all these, or most of these cracks, start allowing particles to move in. And the implication behind this is actually quite big, because in actual situation, we don't expect the pipes to be cracked only at the ground, but rather would be cracked quite all over the perimeter. And in that case, in a dry situation before a heavy rainfall or a sudden rise in groundwater level, for instance, we do not expect all these cracks to be allowing water or allowing sand to infiltrate. But once water is there, we can see that we get a sudden activation of these cracks. Now, with the fact that they both get mobilized and they will both result in higher extent of the final erosion, these inclined cracks, well, in our opinion, they are more critical and more dangerous than the active visible ones. So eventually, we wanted to check on the effect of the sand layer thickness, because remember, one of the reasons and the rationale behind taking this track of analysis is the Freefall arch regime, which basically says that regardless of the sand cover, the flow or the sand flow will almost be constant. Now, we wanted to verify this, and because, you know, just to make sure we didn't waste our time, or there is nothing, or there's something entirely different going on. So here, if you can see that for different sand covers, the times it takes to have the crack exposed vary significantly, right? But this is not the part we're interested in. What the part we're interested in is the straight line segment here, which is the sand infiltration before the crack gets exposed, and we have this rolling regime, right? So if we zoom into that, we almost get the same line slope, or the same infiltration rate, which is very interesting, because now we know for sure that even underwater, we still have this forming and collapsing and reforming kind of dynamics that we have. They are different in quantification than those in the dry case, but eventually and in concept, they are pretty much the same. Well, that is all I have for you today, and I honestly hope you enjoyed this as much as I did, and thank you very much.
Yeah, of course. It's impressive work.
Thank you.
كالمعتاد يعني.
Thank you.
Dr. Abbas بيقول at the end of this nice lecture, how stable or variable are the soil parameters with time due to water or drying effect or change in soil structure and its effect on the operation of the buried or underground large structures?
Oh, that's a very big one. So here we're only scratching the surface, right? So if we are going to confidently give any judgments on the behavior, I think the experimental work would be more capable of that. But as we express more towards advanced numerical tools, we will have to take even numerical samples, because this is very flexible. would allow us to, after the erosion process, to take apart and do some maybe triaxial tests or whatever kind of tests that we do. But overall, in this framework, until now, we're only scratching the surface. So I'm not sure if we're in a place to issue judgments about the cyclic effect of drying and wetting of the soil, or the structural. We actually did in our group some of the, in fact, most cited work and on the structural effect on the nearby structures. But this requires a further step of coupling. So as for now, we're only narrowing the scope to the infiltration process, the rates, the extent of erosion. And as we go further, we kind of hoping to expand that to tackle more, actually, because this is a very fundamental aspect of research. So we're hoping to move into more practical and more kind of geotechnical / interesting topics.
I would like to comment further, and probably with Dr. to be Mahmoud Ali. I hope that this would be extended further, as you have said, and I hope to extend it further beyond your expectations. There is another application in the analysis of dams and dam breaches and stuff like that that may get use of such phenomena.
Exactly.
So we hope that you go further ahead.
Yeah,
I would like to be updated on that.
Inshallah. We have a couple of applications under review so far, so hopefully there will be quite impactful when they come out. I'll be so happy to share them with you. And honestly, it is exciting because, as you said, in dam breaching and in actually so many other areas, the potential work that can come out of this kind of modeling, although it's kind of challenging to begin with to set up the model. But once you're there, it is, it kind of turns your head what you can do with the amount of data you can get from, because we have access to every particle in the system. That's
good work.
Yeah, that's a lot of power. Thank you.
Good work.
Thank you. Any other question? If no, thank you, Ahmed. It was nice day today. Thank you. Impressive work as usual.
Thank you. I really apologize for coming late. I wanted to attend the other presentation so bad.
No worries.
I was under the impression that we're going to start at 3 p.m. So
هي المشكلة في المواعيد الفرق التوقيت
all over the place. Yeah, معلش.
الحمد لله، نورتنا النهارده، نورتونا جميعا، ورمضان مبارك عليكم جميعا، ويجزاكم الخير ان شاء الله يا رب. حبيبي، شكرا،
جزاك الله خير يا محمود.
الله يكرمك يا عبد. كل عام وانتم بخير. السلام عليكم.